So here we can see what our two basis functions look like for ramp functions. Our first basis function will be the blue one with the subscript 0, and that's simply equal to 1 minus x. The other function, psi1, will be equal to just simply x. So if we look at our linear combination of basis functions, our resultant is likewise linear. We can see here the largest term is x, and here the largest term is x, and they're added together. So therefore, our solution approximation is going to be linear. So we could imagine that we have some output that we'd like to achieve. So imagine that this is some value q sub l, and this is some other value q sub r. We can see that the amplitude of both of the ramp functions are equal to 1. So a sub 0 is going to be multiplied by this magnitude here, 1. So whatever we multiply our first ramp function by in terms of a coefficient will be equal to the output for the solution approximation. So we can see here, if we'd like to achieve QL, we simply need to set a sub 0 equal to QL. Likewise, we can see that whatever we choose for our other coefficient, a sub 1, for our second ramp function, that will likewise be the solution approximation output at the far end of the domain. Here we're having our element ranging from 0 to 1. So in this case, if we'd like to achieve q sub r, we just simply need to set a1 equal to that. So we can see it's very easy to get a desired output of this from the two ramp functions. So it's clear what's happening at the two edges of the domain. What about the area in between? Well, we can see that at any particular point along our solution approximation, even though we've only specified two coefficients, our solution is actually defined everywhere within the element. And if we look at that particular point there, we can see that we have, in this case, our first function decreasing and our second function increasing, but that the sum of them together will be equal to 1. And it actually holds true at every single point. We smoothly drop off the impact of the first point and smoothly bring up the impact of the second point, such that once we've fully transitioned from the left side to the right side, the left node no longer has any influence on the right node, and vice versa. So it's easy to see how we could generate a desired output. But what if we'd like this to match some sort of actual function? So we could imagine we have some analytical solution that looks perhaps something like this. Well, we could choose to interpolate that function. So in other words, we'd like to simply have the solution approximation at the element boundaries be equal to the actual solution at those boundaries. But you can see here, if this is our analytical solution, this fit is not particularly good. For most of the element domain, our solution is actually greater than our solution approximation. So the alternate way that you could potentially generate your solution approximation from analytical data is to instead attempt to minimize the distance between your analytical solution and your solution approximation. So you can imagine this mostly straight line here is a potential other choice for a solution approximation. It clearly doesn't interpolate our function at the endpoints. However, it would appear, qualitatively anyway, to be a better fit for our analytical relation. So it's easy enough to see how we would try to achieve our interpolation, but how would we go about trying to get this best fit line here? Well, one way we could do it is that we could require that whatever the inner product of our exact analytical solution with our basis should be equal to the inner product of our approximation, so let me call it f tilde, with respect to our basis. We have an analytical relation, so clearly that can be explicitly defined. We've explicitly defined what our basis is, so we have two analytical functions we can perform this integral. Likewise, we have our basis over here, and we also have an analytical expression for our solution approximation. So again, this can be analytically determined. However, in this case, this will be dependent upon our coefficients. So if one were to solve this equation for the coefficients, then you would receive a linear system where the unknown vector are your coefficients. So you'd be able to calculate what those would be, and in turn calculate what your arguably better fit than the interpolation.